Hey guys, welcome to my channel. I'm LeetCoder, and today we have an amazing problem for you guys, man. We're gonna be going over something very, very nice, right? So let's quickly read the problem statement, guys. So it says the problem is called all node distance k in binary tree, right? So very, very good. So it says given the root of a binary tree, right, the value of a target node named target, right, in the integer k, right, return an array of the values of all nodes that have a distance k from the target node, guys, right? So this is a very, very easy to understand problem statement, right? So they're asking us to find the nodes that are k distance from a particular node target, right? I'm saying. So we're given a binary tree, right? So we need to know the data structure that they're giving us, right? So it's a binary tree. Okay, we're following so far. So it says we may return the answer in any order, right? So whatever, all the nodes that are k distance away from the particular node, right? It doesn't matter the order that you return them in. We are good, right? So you just can see this example, right? We have a nice looking binary tree, right? I'm saying it's a very nice one. So it says that the root, guys, right? The root, we get the root node, right? Which is 3, right? So and we're given a target, which is the node 5, right? This node right there, right? And the k value, which is the distance. Those are the values that are, those are the nodes that they have interest for, right? So we need to find a way to return, guys, right? Okay, so for this example, right, I'm saying all the nodes that are distance of 2 away, right, from 5 are pretty much, 7, 4, and 1, right? We could easily eyeball it, right, I'm saying. So you can see 1 is 2 distance because you got 1, 2, right? It's 2 distance, right? On 2 edges, right? And there's 7 and 4, 2 edges, right? I'm saying 7, 4. But you see that 1, 2, 3, or you see 8, right? Is not included, or 0 is not included, guys, because guys, those are distance 3 away, right? If this was a 3, then we would have included 0 and 8, right? And that would be about it, because 6 is 1 distance away because there's only 1 edge, right? And 2 is only 1 distance away, so it doesn't fit the requirement that they give us, right? K equals 2, guys. Nope. So we're given a 1 node in the binary tree, and then we got a target of 1, right? And we want all the nodes that is 3 distance away. That's not possible because, guys, there's only 1 node in there. So obviously it's not going to work. So that's how we were able to derive at that, guys, right? So this problem's very, very good, right? So hopefully you guys kind of have an idea of how to, if you guys understand the problem I'm saying. So hopefully it makes sense, right? So how can we go about it, guys, right? I'm saying. This is interesting. So they want all the nodes that are k distance away, right? This is a binary tree, right? And we're kind of comfortable with binary trees. I'm saying we've done a lot of problems on this channel before on those kind of, I'm saying in this kind of data structure, right? So we're pretty familiar. So now we could easily find all the nodes right there. I'm saying, so this is, so we're gonna be given that binary tree, right? I'm saying, and then the target node can be anywhere on the tree. I'm saying, so 5 and it was like, no, the second one, I'm saying. So 5 was right there, I'm saying. So now we can easily find, I'm saying, descendants of a particular node, I'm saying. Like we could easily just keep traversing because we got pointers to the nodes. You got pointers to a subtree here, I'm saying. We could easily do that because we have the pointers to a left and a right child, right? So we can keep visiting, right? So what we could do, so we could, if we have, so let's say we're given a target 5, right? The nodes right there, so we can pretty much do, let's say, depth first search and pretty much do a +1 every time we recurse on our child node. You know what I'm saying? So this 5, right, would go. So let's say, if it goes left, right, goes left, it goes +1, right? So now if we do 0 + 1, so now 6 would be 1 distance away, right? I'm saying, so that we can know that. So we have a distance variable that as we're recursing, I'm saying, on our children, right? We do +1 to account for the edge, right? I'm saying, to know that, to increment the distance variable, right? So so from 5 we +1, and then now distance 1 away, and then we go here. Then from this 2, right, it's gonna recurse on the left child, right? I'm saying, and then do +1. So now k equals 2. And then we know that, okay, k equals 2. So now we know that this node should be in there, right? I'm saying, so we add that node into our thing because the distance that it equals 2, which is the distance that we care for, right? So we account for, right? So we do the same thing for 4, right? So those 2 things can be accounted for, right? So, but how do I take into account this one, though? You know what I'm saying? It's not like we have access to our parent. You know what I'm saying? so that we can just go up there and then just, you know what I'm saying, do all those things, right? You know what I'm saying? It's kind of hard. How can we take that into account? We don't have access to our parent node, you know what I'm saying? Because we have access to a left because we have a left pointer and a right pointer, right? There's no such thing as a parent pointer, you know what I'm saying? If that we had that, that probably could have helped us, right? Because we could have traversed, go up, you know what I'm saying, then just we do +1 right there because it's one distance away from 5, right? Which is the source node, you know what I'm saying? And then we do +1 again, and then this would go 2, and then we could say, all right, cool, this node, right, obviously should be included, guys, right? This node should be included in our result because it is the distance 2 away from the target node, guys, right? I'm saying that would be good if that how it was, guys. So how can we go around this? So what kind of logic do we need, right? Since we're talking about pointers, guys, right? We need pointers, right, up to our parent. How about we create that, right? Since it's not already given to us, right? We could say, all right, cool. Since it's not given to us, right? Let's do it ourselves, right? Let's uh pretty much because we're gonna also be given the access to the root, right? The root node, guys, right? Which is important. We're also gonna be access to the root node. So what we could do, how about we traverse the tree, guys, and as we're traversing, guys, we make sure that we also put the parent pointers of all the nodes, guys. So now when we're traversing, we can easily traverse and go anywhere we want, right? I'm saying so this will be pretty much converted into some kind of undirected graph, guys, right? Because we can go anywhere, we can go to any adjacent nodes, right? So for this binary search, there's going to be obviously a left or right and a parent, right? That's all we can have, right? There's not going to be another. I'm saying so we could traverse anywhere, right? So we could go down, we could go up, guys, right? That's kind of the beauty of it, right? So now that we have access to our parent pointer, right, we could traverse, so we could apply those different graph traversal algorithms, right, to kind of solve this particular problem, guys, right? You know what I'm saying? So let's quickly go ahead with the let's kind of see it before we go implementation, right? So we see where I'm going with this, right? So so we gonna pretty much traverse what I'm saying. We're gonna be distance variable to know the distance we are from, I'm saying. So firstly, what we're gonna do, we're gonna have to build our, a map of our parents, guys. So we have a reference to our parent, right? Because a map, obviously, because it gives us a constant time access when we want to know who our parents are, right? I'm saying. So we have reference to that, right? So we just do a parent get my parents. So we get access to a parent, and then we can pretty much visit the parent child node, right? I'm saying, so that we could go in the other direction, guys, right? So from 5, you can do +1 here, there, right? So we're gonna make this kind of interesting, guys. So for this, what's it called? For the for building the parent map of parent pointers, right? We're gonna use the DFS, right? I'm saying, and then after that, guys, what we're gonna do, we're gonna use the BFS, right, to find all the nodes that's exactly k distance away from the node, guys, right? You know what I'm saying? So we're gonna have practice using both algorithms, guys, right? So we're gonna be in pretty good shape, guys, right? So let's go ahead with the implementation really quickly, guys. So yeah, guys, let's go ahead with the implementation, like we said. So like I said, guys, we're going to have a map, right? That's pretty much gonna be the map that's gonna keep track of our parent, right? Because this is a binary tree. We don't have access to our parents, I'm saying. So we need to build that ourselves, guys, right? And that's exactly what we're gonna do, right? I'm saying we're gonna quickly do it with quick DFS. So I'm saying that's gonna take care of that for us, right? And then we're gonna be implementing the logic, right? So BFS. So we're gonna do parents. We're gonna allocate memory for it, right? That's what we're doing right there. Okay. So DFS, we're gonna be all parents. So we're gonna pass in the root, right? And then originally, the root doesn't have any parent, right? Because that's the root node of the banner tree, right? So that's what's gonna happen here, right? So let's quickly implement DFS, right? I'm saying, so we don't forget about it later on, right? So we're gonna do a DFS, right? We're gonna pass in our tree node, and now we're gonna pass in our parent node, right? I'm saying parent, right? So now what we're gonna do, if node is null, no, we need a base case for our recursive calls, right? We're gonna return, right? Otherwise, guys, what we're gonna do, we're gonna do int. Oh no, we're gonna do parents that puts put the node and we put the parent, I'm saying, in there, right? The access to parent, right? And then we just just recurse down on our children guide, right? So with that left, and now the parent, right? It obviously is going to be this root, right? You know, this current root that I'm on right now, right? I'm saying I'm going to do the same thing, right? Read that right, and then now the root, this root that we're on right now is going to be the parent to my child node, right? Hopefully that kind of makes sense, right? I'm saying, so after we do that, guys, what we're gonna do now, we did DFS, right? That's pretty classic, pretty easy. Now let's quickly implement the BFS that we talked about, right? So we're gonna need a queue, guys, right? I'm saying the queue to help us in the BFS, right? So after we do that, guys, so we got the queue. Also, we're gonna need some kind of a set guide, because remember when we did I'm saying when we do the graph problems, right, we also have some kind of set or some kind of data structure to let us know if a node has been visited before, right? So this is standard, I'm saying, graph stuff, right? So if you have, as I know what I'm doing, please check out my graph playlist. I'm saying it's coming out pretty good, so please check that out. So we're gonna have a set of tree nodes as well, right, to help us in efficiently knowing if a node has already been visited, right? So we're gonna pretty much do that right now. So it's set, okay. Okay, so now it looks pretty good so far. So what we're gonna do, so now we're gonna add our node. I'm gonna put so I'm gonna have a paired data structure that's gonna have the node and the distance that it is from the target, right? So that I can easily tell if that node has a distance of 2, right? Then I could easily, or distance of k, right? Then I could easily say, all right, cool, this node should be included in my output result, guys, right? So let me put a paired data structure, right? I'm saying, okay, pair, tree node. And we're gonna use the, what's it called? Integer, right? The distance. All right, so we're gonna pass in new pair. We're gonna pass in what, guys? We're gonna pass in the obviously the target node, because that's the source node, right? That's the node we're gonna be starting from to do the BFS, guys, right? You know what I'm saying? So pretty standard now, and then obviously it's gonna be distance 0 away, right? And we do a set, guys. Set, we're gonna put in the target, right? To say that, hey, this node has already been visited, right? After that, guy, we do a while loop, right? So pretty standard so far. So if the queue is right empty, so if the queue is not empty, right? What we're gonna do, we're gonna pretty much do tree node. No, it's not a tree node. We're gonna do pair. Just copy that, just pretty much copy and paste right there. So I'm gonna get the data from the queue, right? So data is equal to queue that pull. So what we're gonna have the tree node. It's gonna be the key, right? It's gonna be data that get key, right? So I'm getting the, right, and then the distance, right, is going to be data that get value, right? Okay. So after I do that, what's going to be next, guys, right? We're going to have so the pair. So we get that. After that, what we're going to do, we're going to pretty much do a check right there. If the distance of that node, guys, then we just put out the q equals k, right? If that is the case, then obviously I'm going to need a, what's it called, integer, right? At least some integer, right? It's going to hold the values, right? I'm saying the output that we need, right? So new array list, right? Okay, so after we do that, right? So distance equals k. We add res that add the node that value, right? The value, I'm saying, and then just continue after that, right? On to the next node, I'm saying. And we do some checks right there, guys, right? So now, so that's not equal to that, right? So now we need to visit our, the children, right? I'm saying, left and right pointers, right? So we need to visit those as well, right? So node that left is not null, right? And so another check that's important, guys, right? We need to make sure that we put a set, right? I'm saying we haven't visited yet, right? So the set is going to let us know if we have not visited yet, right? So if it's not been visited, then obviously please visit it. So we're gonna put it to that left, and also gonna put it in the set, guys. Make sure that, hey, it's already taken into account, right? Okay, looking good so far. So we do a copy and paste code for the right, or the right node, you know what I'm saying? Hopefully you guys are still with me. All right. So what's next for us? So now we think, right, we're good, right? You know what I'm saying? So remember that, guys, that we said that we also, so for 5, right, it would go, so my left is not null, see, so I put 6 in there, all right, and I put in a set, and I do same for my right child, right? So now, guys, remember that also we need to visit our parent guy because we need to go to visit all the nodes that are, you know what I'm saying, we're counting the edges, right? So we need to go up, and then, you know what I'm saying, and for my parent to visit, if it has any parent, to visit their parent or to also visit their children, right? So we need to take that into account. So what we're gonna do, we're gonna make sure that we visit our parents, right? Hopefully I made clear the reasoning behind why we need to visit our parent guide. Hopefully that kind of makes sense. Yeah, so what we're gonna do, pass in the, so no, I'm tripping. So get the parents for that node. We're gonna do the same check here, guys, right? I'm saying, parents not null, right? And then, yeah, we do the same thing, guys. Copy and paste, simple. And after we do all of that, guys, we should be in good shape, man. This is a lot of code that we've written. Looks pretty good so far. I'm saying it doesn't look like we missed anything important. So it looks like we, we initialize a parent, you know what I'm saying? Hash map, because that's gonna hold the access to a parent, right? And then we have a queue to start our BFS, right? And we did a DFS obviously before so we could get the parents pointers for the nodes, right? And then we have a while loop, right, to start BFS. And we put in our, so we get this every node out of there, right? If the distance of the node is, so obviously I'm missing something. You see, new pair. I need to increment the distance, right? Because obviously I'm forgetting that, right? So distance plus 1, right? Whatever distance that node is, just plus 1 from it, right? You know what I'm saying? And yeah, man, we do the same thing for this one. And we do the same thing for this one, guys, right? You know what I'm saying? So this time it's parent. You know what I'm saying? And yeah, I think we're good. Let's see, man. Data that get key, guys, right? Key. We're getting out a spell. It's not a map. Obviously, it's parents. Oh man, root. No, I'm saying, oh, horrible, horrible, horrible. But you guys understand the logic. The logic is sound, right? So we do a DFS to get, to traverse the tree to, we could have done a BFS as well, right? It's up to you what you want to do, right? So we do a DFS. After we do DFS to get the parents, we do a BFS, right? I'm saying pretty much to the shortest distance, right? It's normally good when you want to find this kind of things, right? Use a BFS, right? Because it's more efficient. All right, so everything looks good, guys. Let's press submit. See if we pass all the test cases. Awesome, guys. We were able to pass all the test cases, guys. So if you guys found value in this video, make sure to let me know in the comment section, guys. If you guys are new here, make sure to subscribe because I'll be doing a lot of other videos just like this one. So thank you guys for watching, and I'll see you guys in the next one.